All right. So it's kind of appropriate that we're turning to look at static electricity as the weather turns cold. They go together. I hope that's something you've noticed. When it's cold outside, the air typically doesn't have very much water vapor in it. It's relatively light on water, and that means that there's relatively little. The number of water molecules in this room is lower than by far than during the summer, and that means that the number of water molecules on surfaces is relatively small. Believe it or not, all the surfaces in this room have some amount of water stuck on their surface. It's just less during in the low humidity times of the winter, and that makes static electricity keeps static electricity in place longer, so you notice it more. So that's just a little aside. But the main thing is that you all have at some point or other noticed static electricity. It's hard to miss. It's particularly noticeable when you do things like dry clothes, and if you put a dryer sheet in, they tend to be relatively less staticky. But if you don't put the dryer sheet in, you tumble the clothes dry, you get rid of all the moisture, they tend to hold on to static electric charges a long time, and they're snapping and crackling as you take them out of the dryer. They stick to each other, all kinds of interesting stuff. So what other things about it? You know that static electricity has the potential to cause shocks. When you accumulate a lot of it and go and touch something and it jumps off your hand onto something else, you feel that flow of electric charge through you. It also can make your hair stand up. That's relatively rare you don't get a lot of that except in certain circumstances. If it ever happens to you on the top of a mountain when there's a thunderstorm around, get off the mountain. It's not a good idea. This is basically, if your hair is standing up and you're the highest thing around, you're basically saying, hit me. Not a good idea. Okay, so the story of static electricity then. My 6 questions to go after. The first is really, why do some clothes stick together where some of them repel each other? You take 2 pieces of clothing out of the dryer. Again, no static, no sheet in there. They might lean toward each other and stick, or they might push apart. Something you might notice. Incidentally, the dryer sheet has the effect of keeping water around, believe it or not, in that it's like it's a more humid day. Therefore, you lose the static charge more easily. All right. Okay, so why do some clothes stick, attract each other? Why do some of them repel? And that was sort of the demonstration I got started doing last time at the bitter end of the class, at the end of the class. So let me do it more carefully now. Just give myself some room to move. And everybody sit still for. So to gather some static electricity, I'm going to rub this piece. This actually is Teflon, and I rub it against a silk tablecloth fragment. And the Teflon ends up with a lot of something on it. And I can transfer that something to this little suspended ball. It's suspended by a thread that doesn't carry electricity. We'll get into all that down the line. But the observation is that once I've put whatever it was that it had accumulated on the Teflon onto the ball as well, the two of them hate each other. They're pushing apart. You can see they're repelling. They're not in contact. It's not a support force. It's not a frictional force. It's not gravity. What is it? I mean, gravity is always attractive. This is repulsive. They are truly pushing apart. And this is, well, it's got to do with something that has been given the name electric charge. And these forces, because they're associated with electric charges, are called electrostatic forces. The forces associated with charge that's not moving. That's the static. All right? Just to give them a name. And like all forces, they can store energy. And that, if you remember the big flash, kaboom that I made with the capacitor and the screwdriver, that was releasing electrostatic potential energy, this same kind of energy. Okay, so I have sprinkled whatever it was that I had accumulated on the Teflon rod onto that ball, and I'll set aside the Teflon rod and the silk piece, and instead work with a piece of acrylic and a thin sheet of Teflon. So Teflon's back in the story, but it's not the rod anymore. It's what I use to rub the rod. So I'll get some more of this stuff, whatever it is, sprinkle it on the ball, and now I'm back in that situation where the stick and the ball hate each other. They're pushing apart. So I've evidently sprinkled something that was on the stick onto the ball, and when we have two objects with that stuff on them, they push each other apart. Another electrostatic situation, electrostatic forces again. All right? So then we come up with the question is what I sprinkled on that one the same as what I sprinkled on this one? If it is, they should repel each other and push apart. So I'm getting this to be, this little demonstration to be compelling. I stop these guys from swinging without messing up their charge. No swinging. So I want to move them slowly together and see whether they repel. They didn't repel. They actually attracted one another. They went together and kissed. And once that happened, they sort of lose interest in each other, which I guess somehow is probably a statement of whatever. The point is, they had something different. The one on your left, and the one on your right, they had something different on them. That when they got near each other, they actually attracted. And what this is that ball that I touched. I'll bring them apart for a second. The ball that I sprinkled stuff from the Teflon rod onto, like this. I'm sprinkling what has become called negative charge onto that ball. The names originate in Ben Franklin. He made the choice. And based on his choice, what I just put on that ball is negative charge. And what I'm putting on this ball is positive charge. So he made the very insightful observation that what they have on them is the same thing. It's charge. It's the same physical quantity. But that one has a negative amount of that stuff, this charged stuff. And that one has a positive amount of that charged stuff. And so while they negative charge on this, the negative charge on that ball and the negative charge that's on this piece of Teflon, those repel each other. So so-called like charges, the same kind of charge, both negative, they repel. Similarly, like charges, when they're both positive, repel. But opposite charges, that being negative, that being positive, they attract. All right? What else? It's a conserved quantity. Charge is a conserved quantity. So that I wasn't creating negative charge on that Teflon stick. Instead, I was removing it from the silk. And it turns out that that removal process involves these surfaces fighting over the tiny electric charged particles that live on surfaces, that live in matter in general. And the Teflon fights unfairly, and it steals negative charge from the silk, so the silk ends up with positive charge. I mean, it's hard to play with the positive charge on the silk. The rod is pretty clear. But the point is that you can't make negative charge out of thin air. You have to take it from something else. And the consequence of taking negative charge, that is a deficit of charge, if you will, from some surfaces, that you leave it with an abundance of charge, a positive amount. So you're just moving the stuff around. Yeah, so at the end, it's a single conserved quantity. You can just have, you can have objects that have a positive amount of the stuff, and you can have objects that have a negative amount of stuff. The overall charge of some isolated object, for example, the Earth is mostly isolated. The overall charge of the Earth is basically constant. It's not quite isolated. We're exchanging charges with the world around the solar system, but pretty steady. You okay with the idea of a conserved quantity known as charge? It charges positive amounts of charge or negative amounts of charge both repel. They repel themselves. Like charges repel. Opposite charges, positive and negative separately, attract. General observation. What point do I want to mention? Yeah, okay, later. All right. So why do clothes not normally attract or repel? And the answer is that most clothes, you just leave them around, they develop exactly zero charge. And why would that happen? Well, if you've got something that has suppose that you throw a sock on the table and it's got a positive charge for some reason, it is going to be very attractive to any nearby negative charges and repulsive to any nearby positive charges. So if some negative and positive charges happen to come wandering around, they'll get attracted, and the positive. What did I say? What did I say what the sock was? Did I say positive? I forget. It's going to attract the opposite charge, whatever that is, and tend to accumulate it, and therefore cancel out it. Gradually lose its difference from zero charge. If it's positively charged, it's going to try to accumulate negative charges that go by attracting them. If it happened to have been negative to start with, it's going to tend to attract and therefore accumulate positive charges. So it's going to tend towards zero. However, getting to exactly zero would be very, very difficult and very unlikely if charges came in every possible value. Because suppose it started with 10 units of positive charge. It has to accumulate exactly 10 units of negative charge to strike what's called electrically neutral, no charge. Is that okay just to define electrically neutral? If a charge goes wandering by it's 3.77221446 negative charge and sticks on it, it's going to now have this horrible 6 point something or other charge left. It's going to try to find more to cancel. The likelihood that it will get to exactly zero is just tiny. It's not going to find the right little pieces to exactly finish the job of getting to zero. Are you okay with that problem? That if charges came in every possible value, finding the right collection of canceling charges that add up to 10 exactly is hard. Too many possibilities. But they don't come in, charges do not come in every possible value. This is a relatively modern observation, like in the past 100-ish years, that charges actually come in discrete portions that are known as the fundamental units of charge. They are associated with subatomic particles. I mean, where does charge come from? Where does it live? It lives on subatomic particles. The particles that you've heard tell about, like electrons and protons. Electrons, which are the particles that live on the outside of atoms, that form the outside of the atoms and that give the atoms their chemical characteristics, those electrons have, and it's a story, one negative fundamental unit of charge. It's a tiny amount of charge. You wouldn't notice it if it was on you, but it's different from zero. It's a little bit less. Okay, it's a little negative charge. And protons have exactly the same amount of charge, but it's a positive amount. There's another constituent of atoms that you've heard about called not neutrinos. Say it right. Neutrons. Why are they called neutrons? Because they're neutral. They have no charge. Neutrinos is something else. So electrons have a negative fundamental unit of charge. A proton has a positive fundamental unit of charge. And just to give you an idea of scale, the metric unit, the SI unit of charge is known as the coulomb after physicist Auguste Coulomb. And 1 coulomb it's actually a pretty large amount of charge. You don't usually get a coulomb around at one time, but you get a good fractions of a coulomb around. The charge on 1 proton is like 10 to the minus 19 coulombs. It's really dinky. But if you have a lot of protons, you got a lot of charge. And electrons, again, about 10 to the minus 19 coulombs, but negative charge. Okay? So charge is found in nature only in discrete portions of these fundamental charges. that has the consequence of allowing things to get to exactly neutral, because they're not working with any possible value of charge. They're working with these discrete chunks of charge. And so if you look at a sock that has a certain amount of charge, you know, it's got an entire coulomb, let's say, to start with, of charge, which is a lot of charge. It has to just simply accumulate about 10 to the 19th electrons that come by to cancel out its charge. When it's getting close to 0, it's going to need 4 more electrons, 3 more electrons, 2 more electrons. Bang! It gets down to 1 and 0. Done. It gets to 0. At that point, nobody cares about it anymore, and it tends to stay at 0. All right? So most objects can find the wandering particles coming by carrying charge, either positive or negative, until they reach 0. That's why when you get something with static, a lot of static and statically cling, you just set it out there and you wait. And it turns out even the air has wandering through it. Sometimes I remember the number. I think it's on the order of 2,000 charged particles per cubic centimeter. I think that's about right. Just there spontaneously. They're not for no reason. They're there actually because of cosmic rays. They're there because the universe is a busy place. And there are things whizzing past us all the time. And they create charged particles where otherwise there wouldn't be any. And those little guys wander around, and if your sock started off with positive charge, it's going to attract some negative charges until it's happy. Okay? So, now I want to come back to that. I want to say first about Franklin. Franklin recognized, Ben Franklin, the statesman Franklin, the scientist Franklin. He figured out, yeah, sure, we got electric charge. I mean, he wasn't working completely out of context. There are other people that are playing around with this stuff. He observed that it's one. We'll call it. It's one continuous material, conserved quantity. We'll call it has a positive amount, it has a negative amount. He can make an object with one form and an object with another form. He has to make the choice. Which of these two should I call positive amount of charge, and which of these should I call negative amount of charge? It was an arbitrary choice, or so it seemed at the time he made it. It's as though he didn't have Teflon back there. It was invented since. But if you remember, this is the one I was touching with the Teflon. This was the one I was touching with the acrylic plastic, like plexiglass. And he just said, they're opposite charges. One of them is positive, one of them is negative. I've got to make a choice. So he went, maybe he flipped the coin. Who knows? He called that one positive and that one negative. You understand it's an arbitrary choice, or so it seemed? What he didn't have the background to know, it took years subsequently, was to figure out, well, these charges are actually associated with specific subatomic particles. And his seemingly arbitrary choice led to defining the charge on the two important subatomic particles, namely electrons and protons. And he chose this one to be positive, and it turns out that is the one that has lots of extra protons on it. So the protons, therefore, carry what Franklin defined as positive charge. This other one that was touched by Teflon, that has an excess number of electrons. And he defined that as negative. Therefore, electrons carry with them, and have ever since his time, negative charge. That's okay. So far, it seems great. The problem is this. The protons are stuck in the nucleus of the atom. They don't go anywhere for the most part. They sit around watching the action. The electrons are doing all the interesting work in most situations. I mean, except for nuclear explosions. It's all down to the electrons. And the electrons, they move through metals to carry electricity around in the form of their moving charge. They are all involved in chemistry and the interactions between atoms and make things happen. And they're negatively charged. So it's like all these interesting interactions take place by the movement of negative amounts of charge. Well, that's awkward. It's like looking at an economy in which everybody's exchanging money instead of charge, and they're doing it by exchanging negative amounts. So you go to the store and you buy something, and the clerk gives you a negative $5 bill. That's how the transactions are all working. They're all working kind of backwards. It's a pain in the neck. So it was an unlucky choice. It would have been so much easier if Franklin had defined electrons as positively charged, because there's what's moving around. And it's too late to fix it. I mean, it's just cast in way beyond concrete. So we all live with the movement of negative charge through wires, stuff like that. We'll get to it, to dealing with that, but it's down the road for us. All right. Any questions about the problem and all right. So the next question is, we see that we can get charge, and you can accumulate positive amounts, you can accumulate negative amounts. Okay, they're associated with subatomic particles, which have this awkward choice. But how do you actually obtain some positive charge or some negative charge? Your experience is that you rub your feet on something and you get it. But the question here is if you start with two neutral objects, do you actually have to rub them across each other to end up with them charged? How many think yes, they got to rub? How many think no, they don't have to rub? Yeah, probably sets you up to pick. It is no. They do not have to rub. It's not the rubbing that does anything. What it is unbalanced fighting over subatomic particles, particularly electrons. When you touch two materials together, like silk and Teflon, if they started off electrically neutral, that doesn't mean they don't have charges. The Teflon has gazillions of positive charges, but it has the same number of negative charges. I should say fundamental charges. It's got gazillions of protons in there, providing gazillions of fundamental units of positive charge. But it has an equal number of electrons, providing the same number of negative charge overall. Okay, so lots of charges, but they balance to zero perfectly, dead on. Same with the silk. When you touch the Teflon and the silk together, and those two surfaces touch, the Teflon looks hungrily at the electrons living on the surface of the silk and steals some of them for chemical reasons. The chemistry of Teflon is more aggressive in grabbing hold of electrons. So you touch them and you pull them apart. The Teflon's stolen some of the electrons from the silk. Sorry, they didn't play fair. You now have net charges. I can show you this now with Teflon and silk, but with, how do I want to do this? Yeah, I'll do it. You did it. Sorry about that. Anyone want a drink? Still works. It'll be fun to watch on tape. All right. So I'm going to put the piece of tape on without rubbing it. Fortunately, for me, it's not like in chemistry class where you break it, you bought it. Ha! I break stuff all the time. Okay, what I did was I put two pieces of just ordinary Scotch brand tape on glass, and the tape sticky surface touched the glass, two pieces of tape. I tried not to rub things, although I was a little distracted by the destruction of glass previously. But basically the idea is I just touched them. And now I'm going to peel them both off, one, and two, and can you see they hate each other? No, don't make us touch. No. Ew, my sister. Ew. Right? Or my brother, to be fair and not sexist. They have the same charge. We don't know what it is, but they have net charges, and they might be both positive, they might be both negative, but they're repelling. So, evidently, these pieces of tape when they touched the glass and the tape fought unequally over the electrons on one or the other. And one of them came off with extra electrons and therefore had a negative charge. And the other, having lost electrons, has unbalanced positive charge on its protons. It's positively charged. Okay? So the point is that the development of these static electric charges, accumulations of charges, doesn't really involve the rubbing. I mean, it seems like you're rubbing off charge. Nah, it's just you're getting good contact between the surfaces. Like when you rub, you get lots of contact. So that's the active ingredient. The charge that you accumulate then when walking across a carpet has to do with the difference between your shoes, the material from which your shoes are made, and the material from which the carpet is made. They fight unequally over charge, and you get one or the other. Yeah, that's basically the story. So in a dryer, with that tumbling motion, in the absence of a dryer sheet, that tumbling motion brings lots of material. Your socks touch everything. They touch, 50 times. If your socks are the thing that most likes electrons in the entire washer, I was probably Gore-Tex. Gore-Tex, incidentally, is it's Teflon. It's what's called it's exfoliated Teflon. It's Teflon that's been puffed, so it's porous. But it's Teflon. I'll bet it steals electrons from everything, and consequently, when you pull out Gore-Tex out of there, it's going to be covered with electrons and everything else. Ha ha ha! It's going to be positively charged. All right. So, if you think back to this question, I asked you last time, and I'll look at it again. When one girl walks across the carpet and reaches out to her twin, who is just electrically neutral, snap, big spark. And now if both twins walk across the same carpet, wearing the same clothes and stuff like that, and they reach out to each other, what's the spark like? Well, I answered this question. Now I can ask it again to see whether you're remembering. How many think the spark is going to be larger? How many think it's going to be smaller? How many think it's going to be the same? Yeah, you're all going for smaller, which is good. It's the same problem as here. The two pieces of tape both had the same experiences. Now it's the two girls have the same experiences. They accumulate the same charge, and reaching out to one another does nothing because one girl's got tons of, let's say, positive charge on her, and the other girl's got tons of, say, positive charge on her. They reach out to each other. There's no advantage for the charge to go from one to the other. They're both covered with the stuff that's going to repel. I mean, conceivably, if they're adequately charged, they push each other away. They reach out. They can't actually touch each other. That doesn't happen. But they won't. The charge has no advantage in spreading out on the other girl. It doesn't. That's normally what drives the charge, drives the sparks, is the opportunity for the charge, for like charge, since the person is covered with the same charge, for it to spread out and get farther apart. The repulsion drives that. All right. Another thought is, what if I do that same thing I did before and I stack the two pieces of tape? So I'll put one piece of tape on my smashed beaker. There it goes, no rubbing. Touch, 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 touch. Everybody's happy. And I put a second piece of tape on top. And now I peel them all apart. I don't know whether I wanted to have it on the beaker or not, but okay, it's okay. Are they going to attract each other? Are they going to repel each other? Or are they going to do neither when I peel this collection apart? How many think that they're going to attract one another? How many think they're going to repel each other? How many think that they're not going to do either? How many are looking forward to the weekend? Yeah. Yeah, that was the major one. I didn't get a definitive value from you guys. So now I peeled them off the beaker, which I probably should have skipped altogether. Now I peeled them apart, and can you see they're attracting? Wow, the one down here, this guy, wow, this is great. The dominant thing that happened was I had basically two pieces of tape stuck together, coming apart, they weren't the same parts of the tape touching. When I put them together, one tape contacted the second tape with its adhesive side, whereas the second tape contacted the first tape with its smooth side. The adhesive and the smooth, they fight differently over charge. And so when I pull them apart, one of them's adhesive layer fights differently over electrons than the other one's smooth layer. So they didn't fight equally. They ended up with opposite charges, which is why they attract each other. Was that followable? I said it about as awkwardly as I can. I could try again to get more awkward, but I won't. All right. Well, one thing that you've noticed is that these charges, which are all around mostly by virtue of things fighting unequally over electrons, they have their effects, but primarily when things are near each other, not when they're so far apart. And so the observation is the attractive forces get weaker with distance, the repulsive forces get weaker with distance. Something about the interactions between charges is distance dependent. And careful study of those forces by Coulomb, for example, observed that the force between between two charges, and they, as always, they come in a Newton's third law pair. So if charge A and charge B, they both attract each other. This one exerts a force on that one, second one exerts a force on the first one. Those forces are equal in amount, opposite directions, all that works out. Those forces are dependent on distance. They're also dependent on the amount of charge, and they're finally dependent on a constant of nature, which has become known as Coulomb's constant. So the force between two electric charges, or assemblies of electric charge, maybe, the relationship is, well, of course, there's a Coulomb constant that gives you establishes the overall scale of the force. And it's big. It's quite a strong, the charge forces are strong. So you have one electric charge measured in conventional units. The conventional unit of electric charge is the Coulomb. So you have a certain amount of charge on one object, you have a certain amount of charge on the other object. If the signs are the same, that the product of those two charges is a positive amount. If the sign of those two charges are opposite, you end up with a negative amount. So the force reverses direction as one of the charges changes sign. This gives you the attraction and repulsion trick. If the charges are like, you get repulsion. If the charges are opposite, you get attraction. And lastly, these forces are related to the distance. How so? The forces get weaker as the distances get longer, and they go faster than just proportional to the distance. They weaken in proportion to 1 over the distance squared. It's called an inverse square law, which happen to be common in nature. Gravity follows an inverse square law too. But so the point is that if you take two charges and they're a meter apart, a foot apart, because I can't do 2 meters. Maybe I can get there. A foot apart. Two charges, if they're a foot apart, they push on each other with 1 unit of force, whatever that is. If you go to 2 feet apart, they push with only 1/4 as much force. Double the separation, you reduce the force by a factor of 4. Okay? What else about this? Yeah, electric charge is measured in coulombs. 1 entire coulomb sitting on an object is a lot of charge. On the other hand, it's built out of all these little fundamental units of charge, which are 10 to the minus 19 smaller. And 10 to the minus 19 coulombs is very little charge. So somewhere in the middle is where most ordinary situations show up. Like, so when you rub your feet on the carpet and develop a lot of static charge, you might have, I'm just guessing, but like 1/1,000,000th of a coulomb, or maybe 10 millionths of a coulomb. Not a whole lot. 1 coulomb would be nasty. All right. So you're okay with it, with this law that the forces get weaker with distance. All right. So then that brings up some other important observations, like, what if you have just one charged object and everything else around is electrically neutral? Does that mean there are no forces left? And the answer is no. So it gets very hard these days to get long, straight balloons that aren't like giant. It's really or the ones you do twisting into little animals. These guys are getting rare. I would hoard them, except that they go bad with time. So I happen to know that when the balloon and my hair fight over charge, the balloon steals electrons from my hair. I could prove it with a Teflon and all that stuff, go back to Ben Franklin and stuff. But this balloon now is covered with negative charge. My hair's got positive charge, but that's my hair's business. And this screen is electrically neutral. Nobody's been paying any attention to it at all, right? No, not really. All right. So the balloon stuck to the screen. But wait a second. The balloon had negative charge on it. The screen was electrically neutral. Why did the balloon and the screen, why are they sticking? And the answer to that is that the balloon and its negative charge affect the screen. The screen wasn't without any charges. It just had a net charge of 0. That is, if you add up all its positive charges and add up all its negative charges, they sum to the same amount and cancel each other. What I did by bringing that negatively charged balloon up to the screen was to coax or attract all the positive charges that are in the screen a little closer, because they're attracted. They're there, and individually they're attracted. So they moved just a hair's breadth, fraction of an atomic distance closer to the balloon. That's the positive charges. The negative charges that hate other negative charges are pushed a hair's breadth farther away from the balloon. So the screen's positive charge is now a little closer, its negative charge a little farther, and now notice Coulomb's law. Coulomb's law says the forces get weaker with distance. Happens to go as the square of the distance. That means the slightly nearer positive charges are attracting the balloon, the negatively charged balloon, a little more strongly than the more distant negative charges are repelling that balloon. There are lots of forces around, but if you add them all up, there's a slight net attraction. The positive charges in the screen being closer win, and they attract the balloon. Is that okay? That phenomenon is known as electric polarization. The balloon polarized the screen. The screen doesn't have a net charge. It's still electrically neutral for all, apart from like mistake issues. It's electrically neutral, but it has a positive part and a negative part. It's got a region that's more positively charged and a region that's more negatively charged. The positive region is near the balloon. The negative region is farther from the balloon. So it's got sort of poles, like a north pole and a south pole. There's the world of magnetism we'll come to, but that polarization is the language people use. So the screen is polarized. Are you okay with the idea of polarization? And so electric charges attract, they polarize whatever they come near, and they are attracted to it. So polarization effects are always attractive. So a charged particle is always attracted to a nearby surface. At which point I'll tell you another public service announcement. There have been, probably still available, things called negative ion generators. These little gadgets that sit on your coffee table, and they fill the room with pleasant negative ions, and they clean the air, or so they claim, among other things. Yeah, they do clean the air. They put negative charges on everything that goes by, including dust particles and smoke particles and everything else you don't really want to have in the air. So they make everything negatively charged a little bit. And whenever those dust particles then drift near your wall or your couch, they polarize the couch, they polarize the wall, and they are attracted to it and stick. So your air is being cleaned at the expense of decorating all the surfaces in your room with crud. So if you don't like your white walls, run one of these negative ion generators and smoke. You'll have beige walls or gray walls soon enough. Okay? There are much more effective systems that put the charge on the particles and then deliberately attract them to the oppositely charged surface. Those are known as electrostatic precipitators or electronic air cleaners. And they revolutionized industry, smokestack industries, about 100 years ago. Virtually all modern smokestack industry stuff, coal burning, whatever. For example, If you just let the ash and smoke come out, oh, you get the London pea supers. But with these electrostatic precipitators, you deliberately put the one charge on the smoke and dust particles, and you attract them to where you want them with the opposite charge. You can pull that stuff right out of the air. And fantastic difference in the air quality. We'll, hopefully we'll say the same 4 years from now. All right, you got the story here? Yeah. All right, so now on to something that's a little more sophisticated. When you take clothes out of the dryer, again, having forgotten the dryer sheet, they're all clinging to each other. As you pull them apart, you can hear them snap, crackle, and pop. If not in that context, you've seen this in other cases where you've got stuff with serious static cling. The act of pulling them apart causes them to snap. And you hear the popping sound of sparks. Why is that? And this has to do with voltage. And so voltage is something you've heard the word all your life, and I'm going to try to convey to you an understanding of what it is. Voltage is the measure of energy per charge. That is how electrostatic potential energy, the energy stored in electrostatic forces. So you can have some charge sitting there with no energy available to it, or you can have it. You can do something that gives it more energy, more electrostatic potential energy, stored energy. And one way to do that would be, for example, if you've got a dozen positive charges, you put them very far apart. They don't have a lot of energy because they don't really notice each other. But if you shove them all together, and you do have to shove, you have to do work on them to pack them all together, they hate it. You pack them all very tightly together. Positive charge with positive charge, bad news. They now have more energy than they had before, more electrostatic potential energy. You have increased the electrostatic potential energy of the same charges. Maybe it was 1 coulomb to start with. That's all you had. You now have 1 coulomb with more energy. It has more electrostatic potential energy per charge, since it's the same charge. It has higher voltage. Its voltage went up. Voltage is literally the measure of energy per charge. It is beautifully analogous to pressure in water. The more pressure water has, the more energy it has per drop. It can do things that when it's pressurized that it couldn't do when it was without pressure. Same with charge. If it's got more voltage, it can do things that it couldn't do when it didn't have that voltage. Is that sort of okay? Hope okay? Well, if you take, I don't know, a sock and a shirt. The sock is positive, let's just say. And I'll try to remember and stick with that. When they're very close to each other, because they attract each other, they're happy, happy, happy. Oh, this is good. But as you pull the positively charged sock away from the negatively charged shirt, an act which requires work, because they don't want to come apart. They're attracted. You have to pull them apart. You're investing energy in them. And that energy shows up as voltages. Well, the voltage of the sock, which has a positive amount of charge that isn't changing, no charge has drifted off the clothing, that positively charged sock now has more electrostatic potential energy. It has the same amount of charge, so the energy per charge has gone up. Its voltage increased. And any machine that would measure voltage according to the real definition of voltage would say, yeah, its voltage increased. 1 volt, 2 volt, 3 volt, 10 volt, 1,000 volt. The negatively charged shirt, awkwardly, also has more electrostatic potential energy than before, but it has a negative amount of charge. So the energy per charge, where charge is positive unless you say otherwise, is a negative amount. It has energy, lots of it, but it's per negative charge. So that's a negative energy per charge. That's a negative voltage. So the positive charged sock went to positive voltage, and the negatively charged shirt went to negative voltage, and they got dramatically apart from one another. Is that okay? So, if you do work on charge, positive charge, and you accumulate it somewhere, the voltage goes up. If you do work on negative charge and accumulate it somewhere, its voltage goes down because it's a negative amount of charge. Well, to finish, since it's Friday and all that stuff, I want to finish with accumulating a lot of charge. It happens to be negative, but that's not important. This gadget's job is to get a little bit of negative charge, a little bit of negative charge, and then do work on it and shove it onto that ball. And I need to show you another demonstration, which I'll do on Monday, to show you that when you put charge on a ball that's made of metal, the charge goes to the outside and lives there, and it basically has trouble getting off. And this is a new guy. Let's see, how well does it work? There's a rubber belt that will keep carrying charge up to the ball and accumulate it. Yeah, it's got a good dose of charge up there. And the voltage then of the top is enormous. It happens to be a negative voltage, but that's the sad part of Benjamin Franklin's unlucky choice. So that charge is just piled up there, lots of energy per charge, so the voltage is enormous. And if you give it the opportunity to go on you, it will. And since it's all light charges, let me just see if I can get my... So I'm now going to accumulate a whole lot of light charge on me. What I can't tell is, is my hair going up at all? Oh, good. It's like, my hair gets limper as I get older. It used to be pretty wiry. But anyway, I can't pick people by, like your hair will go great. But some of you will have hair that will go like gangbusters out like this. We can do it without you getting any shock. I mean, I'm just playing cavalier here. But I mean, here's cavalier hair, right? So the reason this happens, before we try people, the reason that happens is because it's all light charge. It all goes all over everything, and light charges repel, so stuff goes nuts like this. This guy. Woo! Okay, all right. But the more fun is to find somebody whose hair goes nuts, because there'll be people in here whose hair can go out like a dandelion puff. Anybody want to try this? I'll do it so you will not get shocks. Please, yeah. So people, obviously not crew cuts, but we'll give this a show. So here's the idea: Hunter? No, Shay. Stand on the plastic stool. This will electrically insulate you from the world. Your net charge initially is 0. It's the ball's 0 now because I'm killing off its ability to charge. Put your hand on it and keep your hand on it until I tell you to take it off. Okay? So now you're accumulating charge, and hopefully just give your hair a little shake to try to loosen up. What we can't tell is it's starting to go a bit. It's decent. We can get, yeah, it's getting pretty decent. Yeah, maybe run your hand through it a little bit to facilitate the charge going on. You've got some that are off. Okay, to stop this, take your hand off and then step on the ground, and the charge will leave through your feet. Okay? Another person? See, Shay's fine. No. Oh, come on. Molly. No, Rachel. Yeah. You all can secretly do this after class too, and no one's watching. We'll all turn our backs while you do it. Yet another thing is any sharp points that you have, and we'll show you about this next time. Any sharp points tend to lose charge, so what you wear matters. Okay, now touch the ball. No, there's no charge yet. Now you're starting to accumulate charge. You also can feel the charge accumulating. You can start getting sizzling, like your foot is sizzling a little bit. Give your head. Yeah, so some of your hairs, you've got some they're just popped up. All right, you're good. Okay, take your hand off and just step backwards. There you go. And it goes out through your feet. You can feel it a little bit in your feet. Okay, one more person. Hey, come on. So just to make it clear, this ball, whenever I touch it, it lets the charge leave the giant ball and just run into the ground where it doesn't do anything. So there's no charge on the ball, on the big ball right now. This incidentally is called the Van der Graaf static generator. So you can step on the, and now touch the ball, and I will now let charge accumulate. Yeah, you can feel the sizzles. If you've got any sharp object, The charge shoots out of that object. Yeah, you got some loose hairs that are up. What? Yeah, there are a few of them that are up wildly. Great. Okay. Thanks, and just step backwards. You feel like wow. All right, so we'll call it a day. Those of you who are too timid to do it, well, the official class time, we can do it after class time.